And now we take the property number 3. Now what's the statement of property number 3? Prove that an analytic function with the constant imaginary part is constant. With the previous property we saw the analytic function with the constant real part is constant. And now we have to see the analytic function with the constant imaginary part is constant. First we take the let f of z equal to u plus iv be an analytic function by Cauchy-Riemann equation. Dou u by x equal to dou v by dou y and dou u by dou y which is equal to minus dou v by dou x. That means or can write the dou u by x equal to ux equal to vy and uy equal to minus vx. Take this equation, these two equations, take this equation number 1. And now given v equal to c, that means an analytic function whose imaginary, what you have to prove this statement, an analytic function which imaginary part is constant. That means here f of z equal to u plus iv, u is a real part and v is a imaginary part. That means given statement we will take the v equal to analytic function whose imaginary part is constant. That means v equal to c. C is a constant, that is imaginary part is constant. You take this equation differentiating partially with respect to x and y. First we want to differentiating with respect to x. That means v x equal to constant or differentiation of constant value becomes 0. Therefore the v x equal to 0. Again we will take this equation differentiating partially with respect to y. That means by which is equal to by which is equal to constant value is 0. Differentiation of constant value becomes 0. Therefore the vy which is equal to 0. By using the CR equation, you know the formula CR equation, ux equal to vy and uy equal to minus vx. Substitute this formula here. By value, what's the Vy value? CR equation ux, that is ux equal to 0. So what become the value? Vx equal to 0 and ux equal to, what are the values here? Vx equal to 0 and ux equal to 0. You take the f of z equal to u plus iv in this equation differentiating partially with respect to x. Therefore the f dash of z equal to ux plus ivx. That is f dash of z equal to ux and vx value become the answer. Ux value, we got the value vx equal to 0 and ux equal to 0. Substitute these two value here. Therefore the f dash of z equal to 0 plus I0. That is f dash of z equal to 0. Taking integration with respect to z on both sides, that is integration of f dash of z dz equal to 0. Already you know the derivatives and integration cancel. That is f dash of f of z equal to c. So what you have to prove this statement? Analytic function with the imaginary part is constant. That means we want to prove that f of z equal to c. And next we see the property number 4. If w equal to u of x comma y plus iv of x comma y is analytic function, the curves of the family u of x comma y equal to a and the curves of the family v of x comma y equal to b cut orthogonally. Here a and b are varying constant. Or when the function f of z equal to u plus iv is analytic, show that u equal to constant and v equal to constant are orthogonal. You have to prove the orthogonal. Okay. Let f of z equal to u plus iv be an analytic function. By CR equation, again we take the CR equation ux equal to u and uy equal to minus vx. In this equation, take the equation number 1. Given condition u of x comma y equal to a, that is a u of cut orthogonal two curves. U of first curve, we take the first curve u of x comma y which is equal to a. In this curve, by using the total derivative differentiating partially with respect to x and y, that is dou u by dou x plus we have used a function of x and y here. First we are to using with respect to x means dou u by dou x plus dou u by dou y into dy by dx which is equal to 0. Y is a dependent variable of x. That is dou u by dx, we can take the ux plus dou u by dou y can write the uy into dy by dx which is equal to 0. Here want to find the d, we need for the value dy by dx value. That is dy by dx which is equal to remaining value will we get the right side value minus ux divided by uy. So dy by dx is a curve, that is slope that is m1 which is equal to, can write m1 which is equal to minus ux divided by uy. Take this equation number 2. Again you take the next second curve v of x comma y equal to b. Given the statement v of x comma y equal to b. This equation by using total derivatives differentiating partially with respect to x. That is v is a function of x and y here. That is differentiating partially with respect to dou v by dx plus v is a function of y, that is plus dou v by dou y into dy by dx which is equal to 0. Dou v by dx it can be written as vx plus dou v by dou y it can be written as by into dy by dx which is equal to 0. We want to find the dy by dx, that is dy by dx which is equal to minus dou v by dou x. Dy by dx is a slope of the value, that is m2 which is equal to minus dou v by dou x. Take this equation number 3. Next multiplication of 2 and 3. Multiplication the equation number 2 and 3. That is m1 left side value multiplication m1 and m2. That is m1 and m2 which is equal to sorry